So yesterday we studied assignment problem. Today we'll be seeing some more examples of assignment problem. Let's say I've been given this question where you have 3 persons and you have 4 jobs, and there is an additional constraint to solve. The constraint is find the cost from the cost matrix, find the optimal assignment if P3 can't do job 4. That is, P3 is blocked from doing job 4. How would we approach this kind of a problem? If you want to block P3 from doing job 4, one logical thing to do for this is you fix a very large amount or a very large cost for this cell. That seems to suggest that P3 is asking for an excessive amount for doing job 4, which might not be acceptable, because the company wants to minimize the overall cost, and P3 is demanding a very large amount of cost, to do this job 4. So what the company does is, to solve this kind of a problem, it puts a dummy cost that is infinity, or you can also write a capital M, and where M tends to infinity. So you can either write capital M where M goes to infinity, or you can directly write infinity. Now, since the cost is infinity, this placement of infinity would stop us from allocating P3 to job 4. But there is another problem with this question, that the number of jobs in the market are 4 and the people are only 3. So the problem is not balanced. That is, we do not have this condition. The number of jobs is 4 and the number of persons are only 3. So what we do is, we try to introduce a dummy person, say P4, and allocate for each job a cost of 0, 0, 0, 0. That means that dummy person does not demand any price for doing any of the above jobs. If you want to allocate P4 to job 1, he asks you for 0 rupees. He wants to ask you for 0 rupees for J2 also. Similarly for J3 and J4. Now we have a situation where we have 4 jobs and 4 people. Now we can start our assignment problem. So what is the first step? The first step is to find in each row the minimum element. So for instance, this 20 is the minimum in the first row. This 15 is the minimum in the second row. This 17 is the minimum in the third row, and this 0 is the minimum in the fourth row. So what we do is subtract the minimum element from each row. So what do we get? If you subtract from the first row 20 from each element, what do we get? We get a 0 at the first place. 25 minus 20 is 5, that is 5. 22 minus 20 is 2. 28 minus 20 is 8. Similarly for the second row we get 15 minus 15 is 0. 18 minus 15 is 3. 23 minus 15 is 8. 17 minus 15 is 2. So this is the second row. The third row is 19 minus 17 is 2, 17 minus 17 is 0, 21 minus 17 is 4, and infinity minus something is infinity. For the last row we do not have any change because the minimum was 0 and all of the elements are 0. Now we find the column minimum and subtract the column minimum from each of the column entries. The first column has all zeros, at least 1 0, so there will be no change because the minimum is 0. For the second column also you have a minimum entry of 0. Third column also has a 0 in its column. Fourth column also has a 0 in its column. So the column minimum don't give you any advantage. So the reduced matrix remains the same. Now we can try to find the allocations and start doing. How do you do the allocations? If I see a single, starting from the rows, I start from the first row. If I see a single 0 in this row, I mark that 0. And if I mark this first 0, then I also need to cross out any other 0 in that column. So this is the first allocation. I've crossed out the other zeros in that column. In the second 0, I look for a 0. If I find now there is no 0 left to be marked or crossed, so I leave it. In the third row, I see a single 0, so I mark it as allocated and cross out any other 0 in its column. Can I do that for the fourth row? No, because we have 2 zeros. There is a clash, so we just hold it. Now I start this whole process from the column. First column, either a 0 has been allocated or it has been crossed, so I move over to the second column. Second column also we have the same story. Either a 0 has been marked or it has been crossed. For the third column, do I see a single 0 that has not been marked? Okay, yes. So I mark this 0 and cross out any other 0 in its column. So I cross this out. But now you see, I only have 3 allocations. And there is no fourth allocations for this. That seems to suggest that the problem is still infeasible. I need to work towards reaching the feasibility part. How to proceed from this? We have the method. What is the method? I take an unmarked row. And what is an unmarked row? A row in which there is no allocation. So see, there is a second row which does not have any allocated 0. So I mark this row. In the marked row, I look for a crossed 0 and I mark that column. So I mark the first column. In the ticked column, I look for a marked 0. Here I find a marked 0, so I tick this row. Now I can't proceed with this ticking procedure any further, so I stop. Now what do we do? See, this row was not marked, so I passed a line. The next row is also not marked, so I pass a line. Next I pass a line through marked columns. So this is the only marked column that I have, so I pass a line. The whole purpose of this is, as I mentioned in the earlier class, is to cover all zeros on the lines. Any other zero, any zero that you see in this matrix has to come on these lines only. there has to be no 0 that is outside these lines. So next step is to find the minimum in the remaining submatrix. So this is the remaining submatrix that is not on the lines. So what is the minimum in this submatrix? It is 2. Either this 2 or this 2. Doesn't make any difference. So what we do is, I choose the minimum from the leftover matrix and do some steps. And what are those steps? I subtract this minimum from every other element that are not on the lines. This 5 is not on the lines, so I would do 5 minus 2. This 2 is not on the line, so I would do 2 minus 2. This 8 is not on the line, so I do 8 minus 2. This 3 is not on the line, so I do 3 minus 2. This 8 is also not on the line, so I do 8 minus 2. This 2 is not on the line, so I do 2 minus 2. Now once this is done, now I need to check for these elements also. This element 0 is on a single line, so I don't do anything on this. This 0 is also on a single line, so I don't do anything on this. But see this 2. This 2 is at an intersection. So what do we do for intersection? We add the minimum element on the intersection point. So what do? I do a 2 plus 2. This 0 is on the single line, so you don't do anything. This 4 is on a single line, you don't do anything. This infinity is on a single line, you don't do anything. Now this 0 again comes at an intersection point. So what do we do? Add the minimum element. So 0 plus 2. So what do we do for this 0? This is on a single line, so we don't do anything. This 0 also on a single line, we don't do anything. This 0 is also on a single line, so we don't do anything. So by doing this, what we get is this matrix. Now can I do all the 4 allocations? Let's see. Do I see a single 0 in the first row? No. So I just hold that and move on to the second row. Do I see a single 0 in the second row? The answer is no. So I move on to the third row. Do I see a single 0 in the third row? Yes, this is the single 0 in the third row. I mark it and I also cross out any other 0 in that column. Next I move on to the fourth row. By fourth row I see there are 2 zeros, so I just hold this. I move on to the columns. Can I mark any of the zeros in this column? No, because there are 2 zeros, so I just move on to the next column. See, either this 0 has been marked, or this has been crossed, so I move on to this third column. Do you see a single 0 in the third column? Third column also we have a choice, so we hold that. For the fourth column I also have a choice, 0 and 0, so I just don't do anything. Now I see I have traversed the entire rows and I have traversed the entire columns, but even after that I have zeros that are neither marked or neither allocated. So this is a situation of a deadlock. That means we have a certain option at our hand of allocating. And if we want to proceed from this step, we'll have to arbitrarily break the tie of allocating a 0 at some of the places. So what we do is arbitrarily mark either this 0 or this 0. And let's see if marking one of these zeros gets us back to a good position. So let's say I mark this 0. So if I mark this 0, I cannot allocate this P1 to any other job because I've allocated this job P1 to J1. And similarly, J1 also cannot be done by any other person, so I cross out any other 0. This was this. Now start the whole process. Look for a single 0 in the second row. Do you see a single 0 in the second row? Yes, we see a single 0, so I mark it and cross the other 0 in that column. Do I see a single 0 in the third column that hasn't been marked? It has already been marked, so I move on to the fourth row. Do I see a single 0 in the fourth row? Yes, I do. I mark this and I have to cross any other 0 in this column. Since it has already been crossed, so I don't do anything. Now see, I have a total of 1, 2, 3 and 4 allocations. Now once I have 4 allocations, that means I have reached retaining the feasibility. That means the optima has been reached. So what is the final allocation? P1 does job 1 because of this. P2 does job 4 because of this. P3 does job J2, which is this. P4 does job 3, which is this. And what are these costs? These are the costs that they originally demanded, which was in the original matrix. The overall sum is 54. Now see, to arrive at this answer, we had a choice in between. Either to allocate this 0 or to allocate this 0. I chose this and I got this 54. Now suppose I had chosen to allocate this 0, what would have happened? See, this was our matrix. This was the allocation, the only allocation that we could do. Now let's say I mark this 0. So I have to cross out this 0 and this 0. Now proceed. Do I see a single 0 in this row? The answer is no, so I go back to the third row. In the third row I already have an allocation, so there is no need to do anything. I go back to the fourth row. Do I see a single 0? Yes, I do. I mark this 0 and cross out the other 0 in its column. I have done with the rows. Now I start reversing from the columns. The first column I see a single 0, which is this place. I mark this 0 and I cross. Since it has already been crossed, so there is no need to do that. Now you can see there are 1, 2, 3 and 4 allocations. So what is the allocation? P1 does job 3. P2 does job 1. P3 does job 2. And P4 does job 4. And if you sum these costs also, this also comes out to be 54. So this is the case of an alternate optima in assignment problem. Now let's suppose we have another problem with a different set of constraint. And what is the constraint? The constraint is that P3 is assigned J4. So we have a problem in which we already know that P3 is assigned job J4. So how do we tackle these types of problems is, now once we know that P3 has to do job 4, that means it is no longer a part of our algorithm since it has already been pre-decided. So what we do is, you delete this row and delete this column from your problem that you will solve. So what we do is, after removing this row and after removing this column, this is the sub matrix that we are left with. So how many jobs we are left with? We are left with 3 jobs and 3%. Why? Because P3 is no longer a part of our consideration and J4 is also not a part of our consideration. The only jobs that are part of our consideration are J1, J2, J3, and the only people that are left are P1, P2 and P4. So this is the sub matrix. Now we can proceed with our algorithm. Identify the minimum, which is 20. In this row it is 15, in this row it is 7. We subtract, we get this matrix. Next step, what do? We subtract the column minimum. So the first column minimum is 0, so no change. The second column minimum is 3, so there would be a change. You get 5 minus 3, that is 2, 3 minus 3, that is 0, 8 minus 3, that is 5. The last column also there is a 0, so the minimum element is 0, so there will be no change. Now once we have done with the finding the reduced cost matrix after the row operations and the column operations, now I start allocating. Do I see a single 0 in the first row? Yes, I do. I mark this and I cross out this. Do I see a single 0 in the second row? I see this 0 single. I mark this and I also would have crossed any other 0 which would have come in this column. Since there is no 0, so I just move to the third row. Do I see a single 0 in the third row? Yes, I do. I mark this. Now see, I have 3 allocations, P1 or P2 and P4. So what is the allocation? P1 does job 1, P2 does job J2, and where is P3? See, P3 was already decided that it has to do job 4. So at the end of this whole process, I add the cost back of 11. P4 does job 3, which has a cost of 7. So this is the total cost, 56. So let's suppose we have this assignment problem. But the question says that the above given matrix is the profit matrix, not the cost matrix that we usually see in the assignment problem. Now we have to find the optimal assignment to maximize the profit. So how do we deal these questions? See, if it were a cost matrix, then we would have applied the normal assignment problem approach to solve this. But now there has to be an additional step that has to be done to convert this profit matrix into a cost matrix. So how to do that? There are 2 approaches to do. First is, you multiply each element in this profit matrix by a negative sign. Multiply each entry by a negative sign. Now what this does is, see, earlier, what was the maximum profit in, say, the first row? It was 28. That means if you allocated P1 to do job 4, you would have gained rupees 28. But now since you have put a minus sign, if P1 were to do job 4, you can treat this entire entry as P1 is asking for rupees minus 28 to do job 4. So that minimizes your entire assignment problem. So to convert the profits into costs, what you can do is multiply each profit by a negative sign. Now the next approach is, what we'll be following is, instead of multiplying each entry by a negative sign to convert it into cost, we can also convert these profits into cost by doing something else. And what is that? In this matrix, identify the largest entry in this profits. So what is the largest entry in this entire matrix? It's 28. So this approach says, from this maximum element 28, you subtract all your profits, each and every profit ij. That means, say for instance, this is the profit in the first cell. So now if we were to apply this thing, what would this 20 become? This 20 would become as 28 minus 20. So it would become an 8. What would this 25 become? 28 minus 5. 28 minus 25, that is 3. What would 22 become? 28 minus 22. So that would become 6. 28 minus 22 is 0. 28 minus 15 is 13. 28 minus 18 is 10. 28 minus 23 is 5. So you do this for the entire matrix. Identify the maximum element. From the maximum element, subtract each and every entry. So if you were to apply this, we have identified the maximum element in the entire matrix. Next step, what we do is subtract from this 28 each and every element in your matrix. So if you subtract from 28 the value 20, you get 8. If you subtract 28, 25, you get 3. If you subtract 22 from 28, you get 6. If you subtract 28 from 28, you get 0. You have to do this for all the entries. So what if you subtract 15 from 28? You get 13, and this 18 goes to 10, 23 becomes 5, 17 becomes 11. So in the next row also, in the last row. Now this becomes your cost matrix for the assignment problem. The next step is to identify the minimum in each row, which is 0 in this row. 5 in this row, 7 in this row, 13 in this row. Subtract from each row its minimum. So the first row there is no change because the minimum was 0. Second row there would be a change, and that change with 13 minus 5, 8, 8, 5, 0 and 6. The third row change would be 9 minus 7, 2, 4, 0 and 10. For the fourth row the change would be 15, 0, 8 and 3. Now we do that for the column also. In the first column you have a minimum of 2. Second column the minimum is 0, so no change. Third column you have a 0, so no change. Fourth column you also have a 0, so you have no change. So what do we do? Subtract the column minimum. So the column minimum would give you 8 minus 2, that is 6. 8 minus 2, that is 6. 2 minus 2, that is 0. 5 minus 2, that is 3. Second column no change. Third column no change. Fourth column you also have no change. So this is the final reduced cost matrix after doing the row operation and the column operation. Now I can start allocating zeros. Do I see a single 0 in the first row? Yes, I do. This is a single 0, I allocate and move on to the second row. Do I see a single 0 in the second row? Yes, I do. Allocate and cross this 0. Now do I see a single 0 in the third row? Yes, I do. Allocate and move on to the fourth row. Fourth row also I have a single 0. I allocate. Now since I have 4 allocations, I'm done. Now what is the job assignment? P1 does job 4, P2 does job 3, P3 does job 1 and P4 does job 2. And what are these costs? These are the costs in the original matrix. See, P1 to job 4. P1 to job 4 is 28. P2 to job 3. P2 to job 3 is 23. P3 to job 1. P3 to job 1 is 19. P4 to job 2 is 15. So the overall profit is 85. You sum these. So that was it. So the next problem states that the above matrix is the profit matrix. Now also we have to find the optimal assignment to maximize the profit, but there is an additional constraint also now. The constraint is that P1 has to do job 1. So we have a constraint that P1 has to do job 1 and also the matrix is a profit matrix. So how do we do? See, the first step is if we know that P1 has to do job 1, we know that the row for P1 and the column for J1 has to be deleted. So the first row and first column gets deleted. And now since we know that the remaining sub matrix is a profit matrix and not a cost matrix, we identify the largest element in the sub array, in the sub matrix, and from this maximum element we subtract all the other elements in our matrix. So what we get is 23 minus 18 is 5, 23 minus 23 is 0, 23 minus 17 is 6. For the second row we have 23 minus 17 is 6, 23 minus 21 is 2, 23 minus 11 is 12, 23 minus 15 is 8, 23 minus 7 is 16, 23 minus 12 is 11. So now this is the cost matrix that we have. Now what we do is identify the row minimum in each row. So this is a 0, the minimum element. For the second row it is 2, for the third row it is 8. Now we subtract. So we get this matrix. Now we do the same thing for the columns. So in the column, the first column we would have no change because the minimum is 0. The second column also we would have no change because of the 0. For the third column we would have a change because the minimum is a non-zero element, that is 3. So we would get this matrix. Now see if we can allocate. First row I see a single 0, allocate and cross the other 0. Second row there is no 0. For the third row I see 2 0, so I put this on hold. Now I start reversing from the column. For the first column I see a single 0, I allocate and cross out the 0 in its row. So it has been crossed out. Now I see I only have 2 allocations. That means the problem is still infeasible. Now how do we proceed? We draw lines and ticks. So we tick an unmarked row. So what row is unmarked? The first row has been marked. Third row has been marked because it has an allocation. The second row is still not marked. So I put a tick. In this ticked row, I find a crossed 0. So I find a crossed 0 in the second column. So I tick that column. In this tick column, I find a marked 0. So this is a marked 0. So I tick this row. Now I draw lines through unmarked rows and marked columns. Now you see all zeros have been covered. Now I look for the minimum element that is not on the lines. So the minimum is 3. The minimum is 3. So what do we do with this 3? I subtract this 3 from every element that is not on the line. So 5 is not on the line, so I would get 5 minus 3, that is 2. See this 4. 4 minus 3 is 1. 7 minus 3 is 4. Now I see the elements that are on the lines or on the intersection. The elements that are on the line would not be changed, so the 0 doesn't get changed. Now see this 0. Is it on a single line or on an intersection? It is on a single line, so we don't do anything. Now you see this 0. This 0 is on a single line, so I don't do anything. The 0 remains as a 0. See this 0. This is on a single line, so I don't do anything. But see this 8. This 8 is an intersection of 2 lines. That means I have to add this 3, the minimum element, to this 8. So that 8 plus 3 becomes 11. Now see if you can now allocate. First row I have 2 zeros, so I just skip it. Second row I have a single 0, so I allocate this and cross this. In the third row, do I see a single 0? No, so I leave it. Now I start reversing from the columns. Do I see a single 0 in the first column? Yes, I do. I see a single 0. I mark this and I cross this. Moving on to the second column. There's nothing to be done. Going on to the third column, I see a single 0. I mark this and end the process. I say I have 3 allocations. The problem becomes feasible. So I just write this. What is this P1 to J1? See, this P1 to J1 was already mentioned that it has to do job J1. So I have just added back the cost. And these are the costs that I found from the algorithm. See, P2 does what job? J4. So see, P2 does job 4. And what is this 17? This is the profit that was written in the original matrix. P3 does job 3. See, P3 does job 3. P4 to job 2. See, P4 does job 2. I add all these costs, I get an answer of 73. So this is all about assignment problem.